The following podcast is sponsored by Structure Tech.
So there's a lot of different components and parts to a house. And if you change one thing, it can really impact another thing. And so it's understanding how all those pieces kind of fit together. And building science is all about understanding the durability of a house, the energy efficiency of a house, comfort for the occupants. It kind of looks at all of those things.
Welcome everybody. You're listening to Structure Talk, a Structure Tech presentation. My name is Bill Ulrich alongside Ruben Saltzman and Tessa Murray, as always, your Structure Talk crew. On today's episode, we are going to do a little vocabulary lesson. And I guess Tessa's going to become the teacher this episode. And we're going to talk a little bit about building science. And so we thought it would be important for people to understand where building science becomes important in the house you live in and where it's not so important. So say hi to everybody, Tessa, because I'm handing this baton off to you right now.
Do you know what you're signing up for?
No, I don't understand building science very well.
Well, I am happy to talk about building science for this entire podcast. You're going to have to stop me when we're out of time. But, I think building science is a term that people probably haven't heard of and may not even really know what it is. So I wanted to just kind of talk about that first. And really, building science it looks at a house and it's this holistic view of understanding how a house works as a system. So there's a lot of different components and parts to a house. And if you change one thing, it can really impact another thing. And so it's understanding how all those pieces kind of fit together. And building science is all about understanding the durability of a house, the energy efficiency of a house, comfort for the occupants. It kind of looks at all of those things. And so really I kind of equate it to like a house doctor. When you think about it, like our human bodies, they're very complex systems, right? There's a lot going on in there. And so let's say you're not feeling well, you go to the doctor. Well, they have a pretty good idea of all these different systems, how they work together, and they can diagnose what's going on, right? And if they can't, well, then they send you to a specialist, right? Maybe a heart doctor or a cardiologist or something like that. Our houses, they work the same. It's a complex system. And so to be able to understand the mechanicals and the materials and the occupant behavior is really crucial to making sure that you've got a house that is going to perform the way that it's designed. It's going to be durable, and it's going to be healthy and comfortable for the occupants to live in. That was a long-winded explanation of basically what building science is, but you can apply it to every single house today. And I think it's a really, really important niche to understand. And I think that the need for building scientists will just continue to grow as our houses get more and more complicated.
So Tess, can I jump in here? You had mentioned some of the critical variables that are in the building science equation. So can we kind of check some of these off one by one? And I was jotting notes like a good student's supposed to in my class. Do you consider airflow to be a component of building science?
It is. So my building science professor at the U of M, Pat Hillman, he says that it's all about the H.A.M sandwich. So H.A.M meaning heat, airflow, and moisture. And if you can control and understand those three things, then you've got a handle on the building science and how a house works.
So then occupant load or behavior becomes a what?
So occupant behavior is just a component of how those three things can be affected. So you can have a family of 5 living in a house with 3 kids, and let's say there's 5 showers a day. The moisture load on that house is going to be much greater than a house the same size that just has one person living there. Maybe they only take 1 shower every other day, right? So the occupant behavior really has a part in how that house performs as well.
So it's a subset of moisture. It ramps it up or ramps it down. That's a bad way to say it, but that's what I'm seeing. Okay, all right. So is it that simple as a ham sandwich where you plug in some numbers to know how good your house is doing building science-wise?
Well, there's a lot of building scientists out there that have a lot of different tools and equipment that they can use to do tests on houses. Probably the most notable one is like a blower door. And if you've ever had an energy audit done before, maybe you've had one in your own house, but it's this big fan that gets installed in a temporary door. And that fan sucks all the air out of the house. And what that tool is used for is to measure how leaky your house is. And how it works is that fan is depressurizing the house. And so it's actually pulling in outside air through all the little cracks in the building envelope. And this fan and these tools can measure how much air is leaking through the building envelope. And so that's one of the tools that can be used. But going back to your question, some stuff with building science, I mean, there are tools out there, but when it comes down to it, it's all about the materials that you choose, how the house is put together, the climate that it's exposed to, and the occupants that are living in it. And so sometimes you don't have all the numbers for the equation. There's a lot of variables. Yeah.
Okay. You can begin to quantify variables through measurement, through building practice.
So one of the biggest changes, you're kind of talking about, new houses today. With building science, the evolution of houses has led to this need for building science because our houses, 100 years ago, were very, very different from the houses we have today. And one of the biggest differences is how airtight they are and how much insulation we put in them. And houses that were 100 years old were pretty drafty, right? And didn't have much insulation in them. And a lot of the materials that were used were very different from the materials we use today. So imagine a house that is built with real wood from trees that are 100 years old, where that wood is just naturally decay resistant. Lots of heartwood was used in the construction of those houses. And if water leaks in around a window in a 100-year-old house, you're going to have pretty good airflow and heat movement through that wall cavity to dry out that moisture. So it's all about heat, all about airflow, all about moisture. So the drying capacity of that wall is going to allow that moisture to dry. But a trade-off is now you've got a house that it's more durable, it gets wet and it can dry out, but it's drafty and it's really expensive to heat, right? So as we move forward through time, we've found ways to make our houses more comfortable and more energy efficient. And how do we do that? By controlling the heat and the airflow. So if we build a house that's much more airtight, there's less air leaking through the building envelope, we need less heat or less air conditioning to make our indoor environment comfortable, right? And that goes along with insulation. So now what happens if you take a house that has a wall cavity that is full of insulation and it's really airtight, and now you get water leaking in around a window. And on top of it, the materials are different too, right? We don't have all those old growth trees anymore. So we're using wood composite products like OSB or fiberboard or, basically wood pulp that's been glued and pressed together. When that stuff gets wet, what happens? That wall can't dry out anymore like it used to, right? So we've got some trade-offs. With building science, it's really understanding how these materials get put together, the durability of a system, managing all of these different things to ensure that you've got a house that's going to perform the way that it should. But we've got these houses that are a lot more energy efficient today and more comfortable, but they're a lot less durable.
All right. Tessa, as a person who owns a new house, what's the most important thing I need to do to prevent problems in this new, tighter environment?
That is a great question, Bill. And I wish I had a one-size-fits-all answer for that. But anyone that knows me and is familiar with building science probably has heard me say this before, but it depends, right? So it's kind of like if you ask me a question like, okay, I'm looking to be as healthy as I can as a person, what type of diet should I go on? Well, it's like, okay, depending on who you are and your body type and everything else, I can't tell you what diet you need to eat. That's going to really depend on who you are as a person. So the same thing goes for a house. You might have a house that is pretty robust in certain areas and you can do some changes to it and it'll be okay. Versus a house that might be kind of teetering on the edge of failure in some areas and you do one little thing and it just pushes it over the edge. Pat Hillman, again, he equates it to how close to the cliff is your house? How close to the cliff? So you take a house that's pretty airtight, lots of insulation, materials aren't as durable, and let's say you install this new window and you don't flash it properly. Well, that house, that wall situation is going to be a lot more likely to fail than if you were to install a window with no head flashing in a 100-year-old house with no insulation in the walls. Does that make sense?
Sure. I'm just thinking back to the days when I once worked in construction, and some of the methods which houses were built then, and I'm afraid for these people and the long-term durability of these structures.
Well, funny that you say that, because I know what you're talking about. I was building houses for a habitat, which I won't name, down south. This was after high school, I did this, and I didn't know anything about houses at that point. I didn't know anything about construction, and there I was building houses. And I remember my site boss told me one day, "You're going to be installing dryer ducts through the outside wall, through the exterior walls." And he gave me this jigsaw to cut holes through the wall sheathing and through the walls. And I was like, "I don't know what I'm doing." He's like, "Well, it's fine. Just cut a hole. And, if you can fit a cat through it, you can caulk it." I just cringe now, knowing what I know about houses and airflow and moisture and all of that, of what I did to those houses. Oh man, it wasn't good. But
and I'm not even suggesting we cut any corners or did anything wrong. I just think there was a lack of knowledge at that time. And so there's probably some gaps in what was done right.
You know what, Bill? There's still a lack of knowledge out there. I think part of that is because of just the way that the construction industry is set up. When you think about it, when you're building a house, you've got all these different contractors that have a part in the construction of that house, right? Well, and the design of it too. You've got someone who is just a designer sometimes. Maybe you've got an architect who's designed something, right? And they're looking at it from an aesthetic kind of perspective. Then you've got the contractors that come in and actually make that dream a reality. And they know how to actually build it and put it together. And then underneath that, you've got all these different subcontractors that specialize in different, areas of building this house. You've got roofing contractors, siding contractors, you've got HVAC contractors, mechanical, involved in that, and all these different trades. And the problem is in our industry is that none of them communicate, none of them talk to each other. They're a master of their one specific field, but they may not know. The roofing contractor probably doesn't know how your mechanical system works in your house. And your siders are not going to be familiar with comfort level and all those other things involved. So there's this disconnect there. So even though we do understand building science now, it's just integrating that into just the general understanding of the public.
What's the benefit of a roofer knowing anything about what the mechanical people are doing?
Well, it goes back to building science and understanding that a house is a complex system of interconnected parts. And so it's like you take your car to a mechanic, and in order to diagnose a problem, they have to understand how every system works in that car. When you're looking at a house and you're wanting to make sure that it is going to be high performance, meaning that it doesn't have issues with mold and rot, doesn't have issues with water intrusion, it's comfortable for the people living in it, and it's energy efficient, well, then it's important to understand how all those pieces fit together, because one thing will impact another. So if your roof isn't working the way that it should, it might lead to water intrusion issues, right? Oh, Ruben wants to say something.
Well, and hi.
Ruben, I didn't even know you were here, Ruben.
Yeah, sorry. We had Steve Kuhl on the podcast recently, and he gave us a perfect example, because he was talking about how when they switch over a client from a wood roof to asphalt shingles, they got to put down different underlayment underneath all of it. And he tells people that the asphalt shingle roofs don't seem to breathe the same way that wood roofs do. And they end up seeing a lot of condensation issues in these roofs when they do the replacement. So he warns his clients ahead of time about this. So, I mean, that would be a perfect case in point.
Ruben, I'm so glad you remembered that conversation, because that's exactly why it's important to understand every component of a house and how it fits together to make sure that you've got optimal performance.
Well, and I got one more example on that. I'm raising my hand here. Tessa's calling on me. I'm being the student today. One more perfect example. I remember there was this guy who was in training. He was the one inspector we lost because he moved to Virginia. This is Greg. Awesome guy. Wait, it wasn't Virginia. It was North Carolina. Okay, Greg, hi if you're listening. But I remember we were going through training, and he was a roofer, and we would regularly get inside of an attic and we'd find the bath fan duct disconnected. And he's going, why does this happen so often? And I'm like, well, when the roofers come through, they take the duct off, but they don't pay any attention to what's underneath it. And they slip the new vent terminal back on when they're on the roof, and they don't know if they disconnected it or not. And it happens all the time. And I could see his face kind of flush. And he's like, I bet you we've done this at dozens of houses. And next time I saw him, he's like, I just ended up calling the last 30 roof jobs that I had. And I'm doing site visits at every one of those to see if I disconnected the bath fan duct. Like,
Oh,
he's an
wow.
awesome
Good guy.
stand-up guy. Oh, yeah, for certain. But just one more example of how, unless you appreciate how the other trades are connected to yours, you're going to screw up their work.
Yeah. That's a great example, Ruben. To that point too, working in the insulation and home performance world for a little while, we used to get called out to houses that had issues with ice dams a lot. And I can't tell you how many times I've been told by people, I've got this ice dam now, but we just replaced the roof last year. I never used to get ice dams before. It's the roofer's fault. And I don't know. Have you heard that too, Ruben, where you go out and people blame the ice dams on the roofer?
Oh, always, always, always. The roofer is definitely the first person who gets the call. We've been hired by a number of roofers to just kind of help defend them.
Yes.
Because we tell people the truth.
Right. Yeah. And we'll save ice dams we've talked about ice dams before. We won't even get into that. But ice dams are not caused by a different type of shingle put on or a new roof. It's all about heat escaping into the attic, warming up that roof and melting the snow. That's what's causing the ice dams. So the poor roofers get blamed for it. And if they don't understand building science, then they might be taking on that responsibility for those homeowners that are complaining. So.
Or you just end up with a lot of unhappy customers that aren't unhappy because it's actually their fault. It's just an unintended consequence of something.
Exactly.
Can I ask you a silly question about airflow in houses, as long as we're talking about building science? My 1940s house has all the ducting running up the trunk, like the center elevator shaft of the house, where newer houses seem to deliver the warm air or cold air at the perimeter. Why the switch?
Well, there could be a few different reasons. I'll tell you what I think, and then I wonder if Ruben, if you can chime in too, if you've got a different opinion. But I mean, if you had an older heating system in your house, if you had like a gravity furnace, that system would heat up air and that air would then rise. There was no fan to push the heat through the ductwork. It would just through convection, the heat would rise and heat the house. And then as that air would cool down, it would fall and then go through the return back to the furnace. With our more efficient systems today, we've got fans that push that air through the ductwork. And, the reason we want to get that heat out to the exterior walls is to make that space more comfortable, because that's where you're losing the heat. So we deliver the heat to that exterior wall to kind of make that space feel more comfortable.
Well, mine's not a gravity situation. We're not that old, but because we have ductwork throughout.
Ben, was there, if it wasn't because of like a gravity furnace situation, why did they initially structure ductwork that way?
I thought it was because of a gravity system.
Okay. I don't know. I didn't know if there were other reasons.
No, that's it.
So I got that really
I've
right.
stumped the teachers. Thank you.
No, she answered your question.
Moving on that.
You just don't know about it, Bill.
All right. So keeping moisture under control, that's a big important thing, and that an occupant needs to do. That means use a lot of fans and stuff like that. What else?
Yeah, moisture really is a big one. Moisture can really have a negative impact on the durability of a house and also just indoor air quality and just the general health of the occupants. So if you've got a house that has mold growing in the walls, or water leaking in, mold growing in the walls, or you've got too much moisture buildup inside with mold, that's not a healthy environment. So controlling moisture is really, really important. It's all about preventing water from getting in from the outside, which Ruben and I teach a 1-hour class for real estate agents about water intrusion issues and all the things we see on houses. That's a huge one, managing that water from the outside.
Yeah, exactly. And I mean, it's a 1-hour class for real estate agents, but it always feels like we are so dang rushed to get through that class. And it feels much more comfortable when we teach the 2-hour version of this to home inspectors. That's about the right amount of time.
You might think, wow, how do you talk about water intrusion for 2 hours? But it's amazing. I mean, there's a lot to talk about there. Yeah. And then from the inside too, you need to think about moisture from the inside. And, we humans generate moisture just from breathing and living and cooking and showering. So controlling moisture and contaminants on the inside of the house is really important. And, the tighter houses get, the more important that ventilation is to maintain good air quality. So in the building science world, we refer to it as IAQ, indoor air quality. And building science basically teaches you build tight, ventilate right. There's a lot of builders out there, contractors, just people in the industry that I still hear say all the time, well, this house is just too tight. They're going to have poor indoor air quality, moisture problems. It's just too tight. And I'll tell you, there is no such thing as a house that's too tight. You want the house to be tight so that you can control that airflow through the wall systems. You want to reduce the amount of air leakage, increase the energy efficiency of that house by making it more airtight. But when you do that, it's really, really, really important to make sure you have some sort of mechanical ventilation system in place to prevent the buildup of contaminants like moisture or carbon monoxide in the house.
Well, one more thing to worry about. Yeah, I see it.
I mean, I could just get into talking about all the pollutants in houses that people are probably unaware of that we live with every day that contribute to making people sick.
That's episode number 2, Tessa.
We'll save that for later. But
small bites of building science.
She told us we'd have to cut her off, didn't she?
I did. You're going to have to cut me off.
All right. Well, we'll take that up on the next episode or maybe a future episode.
A future one, sure.
Yeah. All right. Well, thanks everybody for listening. You've been listening to Structure Talk, a Structure Tech presentation. We will catch you next time.
For more information on how we can provide you with the right information about your home before you buy or sell, contact us at structuretech.com.